Well, welcome to MV Tutors. My name is Figa Manana, and you are very welcome. Today we're doing a topic on electrodynamics. Okay, as you can see from here, this is the type of vision that we're trying to work towards. Now, I like to start my sessions with a vision in mind to know what we are working towards. And these are the types of questions that we will be trying to explore and look for the principles and learn the principles in order to be able to answer such types of questions. Like I said, this is electrodynamics, and if this is what you're looking for, then you came to the right place. Stick around, and by the end of this session, you will understand this topic. Okay. Well, let's get right into it. Well, like I said, we're doing the topic of electrodynamics. First of all, let's start here. Let's start with the definitions of the terms. Now, this word electrodynamics is actually two words that are combined. Electro comes from the word electricity. Okay, just like this, electricity. So there is obviously electricity involved in this. And then dynamics, it just simply means movement. Okay, so it's like electricity movement, right? Or the movement of electricity. That's what we mean when we're talking about electrodynamics. Understanding that term is a very good start, but there are two electrodynamics, what shall I call them, things. Let me just call them things that we shall talk about. The first one is what we call an electric motor. Okay, and then the other one is what we call an electric generator. Okay, so these are the 2 points of discussions that or things that we will be talking about. First of all, what can we understand about a electric motor? Well, let me just put it this way. Let's start with an example of an electric motor. When we're talking about electric motors, we're talking about example things like electric drills. Okay, washing machines, we're talking about electric fans and all the like, things that everyday appliances that you plug into the socket of electricity, and they need electricity to work. That is what we are talking about when we're talking about electric motor. So let us define electric motor. What exactly happens in an electric motor? So like I said, it needs electricity, so you need to plug it for it to work. Okay, let's talk about a fan, blowing fan. You need to plug it in order for a fan to work. So what is it doing? What it's doing is that it's taking electrical energy. And what does it do with electric energy? It turns it to mechanical meaning the movement as well, mechanical energy. So it takes electrical energy and it turns it into electrical energy, and the law that it uses is a law called Lenz's law. Now, you don't need to know in detail what Lenz's law is. All you have to know is that electric motors use Lenz's law in case they ask you in the exam, because what I'm trying to do here is help you to understand what you need for your examination. What is examinable? Should you need further details, you can always read up on it in your textbook. Okay, so let's talk about electric generators now let's start with examples of them. Now, electrical generators, for example, here in ESCOM, in South Africa, we use a service of ESCOM. Okay, so what we're really talking about is power stations. Okay, power station. That's what we're talking about when we are talking about generators. Also, coupled with ESCOM, here in South Africa, we have a lot of load shedding. So when you buy an external generator to supplement the electricity coming from ESCOM, that is an electric generator. So what is happening in an electric generator? What you're actually doing is that you are taking mechanical energy, okay, mechanical energy, and you are turning it into, what does a generator do? It generates electricity. So you're taking mechanical energy and you're converting it to electrical energy. That's what you're doing. That's what you're doing with electric generators. So for example, the mechanical parts, there's lots of them. Just on a sidebar, while we're speaking about ESCOM, to generate mechanical energy uses a lot of coal. So 90% of power coming from ESCOM is coal power. Okay, so they take the coal, they heat it up, there's water involved in there, and then they heat up the water, and then the steam turns the turbines, and then those turbines then conduct electricity, and then they pass it through to you. But also there's hydroelectricity, so, mechanical energy. Hydro is means the involvement of water. So for example, in a river, the river water turns the turbines, and then those turbines conduct electricity. So there's different ways to get mechanical energy. There's also nuclear power, there's just different way. But what I want you to know is that electrical generators, they use the law of Faraday's. So Faraday's law. Okay, so electric generators use Faraday's law. Just keep that in mind and know about it. Okay, so these are the two instruments, or two parameters, or two things that we need to talk about in electrodynamics. Of course, there's always more that we can talk about, but for the purposes of metric, this is all you have to know. Okay, so let's move on swiftly. So right about now, I want us to talk about the actual energies, how they are created. But in order for us to do that, I need us to now talk about what is called magnetism. Okay, let's talk a little bit about magnetism. Yes, you guessed it. It involves the use of magnets. So a magnet always has a north pole and a south pole, right? So that's my typical magnet. Now, if you know about magnets, this is just now a revision of grade 11 stuff. Okay, so let me just draw. Now this is magnetic field. Okay, now the magnetic field is always flowing from what? The north to the south. Okay, so it's always flowing from the north to the south. Okay, just like that. See, from north to south, which means from the north it's flowing away, and then from the south it's flowing into the south, like that. So now this is really the magnetic field. Okay, magnetic field. So this means that if you have two magnets then connected, or rather two magnets with the north pole this side and a south pole that side, these are just two magnets, right? Let me make them a little bit longer. Okay, so it means that the electric field flows from magnetic field flows from the north to the south, just like that, right? Just like that. Okay, from the north to the south. Now you have to know this. It's absolutely critical. So now in this topic of electrodynamics, I want us to talk about this. Is something called FBI. You know, FBI, just remember FBI from the movies and the series you watch from America. I'm sure you've seen FBI, the law enforcement in America. You know, so think of that when you think of magnetic field and stuff like that. So the F stands for the thrust force. Okay, the thrust or the force. Okay, and then the B stands for the magnetic field. Now the magnetic field. You know, whenever I write field, I forget the L. And then the I now stands for current. Okay, so you know, force is always denoted by F, magnetic field is always denoted by B, and then current is always denoted by I. So these are the things that we'll need are needed in order for, let me say, the energies to be transferred or to be created rather, or converted. Okay, these are the things, the variables that you need. Now let's explore them a little bit more. Okay, at this point I will like to start talking about, really, let's just talk about let's start with the electrical motors. Okay, let's start with motors. Okay, remember we were speaking about a fan. It's converting electrical energy into mechanical energy, so it needs to be plugged in order for it to move. Okay, so let me write this statement down. You know, when you take a current, so that's the electricity, a current carrying wire. Okay, and you take that wire and you place it in a magnetic field. Okay, when you take a current carrying wire and you place it in a magnetic field, okay, what happens? A force is exerted. A force is exerted on the wire. Okay, so what does this actually look like? So let me just draw these real quick. Say now I've got a magnet here, Okay, let's put the south this time. Let's make it isometric, meaning making it three-dimensional like that. And then that's a magnet. To create the magnetic field, we need another magnet. I'll draw it on the left, but right in the middle, because remember there's a wire involved. Okay, so right in the middle here, I will draw the wire. Okay, so say the wire like that, just like that. Okay. Okay, so electric carrying wire. An electric carrying wire, this is it. Okay, so it's carrying current, rather current carrying wire. So if that means that there must be something connected to it, like a battery, or you just plugged it to the wall. So it's got electricity, and this is positive this side, so electricity is flowing this way. Okay, flows that way, from positive to negative. Okay, so electricity, I've plugged it there. Now to create the magnetic field, so I need another magnet over here. There we go, I've got a magnet and north. Now this creates a magnetic field, and remember the magnetic field flows from the north to the south, right? Remember that flows like that from north to the south. Okay, now a force is exerted, which means this wire is going to start moving. Either it's going to move clockwise or anti-clockwise, meaning either it's going to move up or down. Now how do we determine this? Okay, how we determine this, I want us to talk, we use what is called the left hand rule. Okay, right now in your left hand you are really going to have, you need, number one, you need your thumb. Okay, and the thumb is gonna represent the force. Remember there's three variables, and then you're gonna have an index finger, and the index is going to represent the magnetic field. And then you're gonna have the middle finger, and your middle finger is going to represent the current. So FBI. Okay, that's F, that's B, and then the current, that's I. Now let me just grab a picture to demonstrate it to you how it looks. Okay, so here we go. I got Fleming's left hand rule right over here, as you can see it. Now let's start with the magnet that they use in this example here. So they've got the north on the left and the south on the right to create a magnetic field. It's moving from the north to the south. So it moves from left to right, and it's represented by the index finger. Okay, so line of flux field, that's a magnetic field. Okay, that's the B. And then if you got current, then current is moving, so this is a 3D shape, right? So it's moving from the page towards you. Okay, from the page towards you, or the screen towards you. Okay, and that is the middle finger. All right, and then moving up, then that means the force will make this wire move up. The motion will make the wire move up. So it's really like this. Okay, so that's your force, line of flux. The current is coming towards me. You see, 3D like that. Okay, now let's look at my example over here. Now let's actually name these. Okay, so if that's A, B, C, D. Now remember, this thing is also in 3D. Now let's look at side AB. From side AB, we are given current. Okay, so we start with the current, which is the middle finger, and it's moving that way, right? And then which way is our magnetic field? Moving from north to south, so it's moving that way. So magnetic field is moving that way. It's moving that way, and the current is moving that way, which means the force from this side, this wire, is going to move up. Okay, so it's going to be moving up. Okay, and then this side, let's look at this side CD. Now the magnetic field is still moving that way. Okay, but now the current is no longer moving into the screen, but it's moving towards you. So the only way that I can keep this left hand orientation is if I turn my hand down like that. Okay, you see now what's happening? My electric field is going that way. It's still going from right to left, and then my current is moving towards me now from the screen, and then which means my really it's like this, which means my force is now coming down on this wall. It's moving down. Okay, so from here this wire is gonna move down. Okay, so as you can see, then what's happening is that this wire is actually turning clockwise. Okay, it's turning clockwise, so we have a clockwise movement over here. Okay, because it's turning clockwise like that. Anti-clockwise would be like that. Clockwise means it's turning like the clock, like the watch. Okay, the hands of the watch always move from 1, 2, 3, 4 like that. Okay, so this wire is also turning clockwise. Well, that's what I wanted to demonstrate very shortly here. Now I want us to then talk about electric generators now. Okay, this one is also we're done with motors. That's what you need to know. Now let's talk about generators. Generators are pretty much long, and remember, generators are turning mechanical to, you guessed it, you said it right, to electrical. Okay, so we've got a magnet once again. Start with the magnets. I've got south. Let's make it three-dimensional like that. Okay, and then you've got your electric wire inside. Same configuration, right? Same configuration. Let's keep the configuration consistent, just like that. And then we've got a magnet again, once again this side. Okay, just like that, and north this side. So what do we know is that the field is moving away from the north, and it's moving towards, you know, the south, really. Okay, so it's moving towards there. Cool. Now what else do we know? Okay, we don't know anything, but what I'm going to tell you is that here we are actually, remember, we're turning the the mechanical into electrical. So what we do then is that we're going to, for FBI, once again, we're going to use the right hand rule. Okay, let me use a different color. We right over here we use what's called the right hand rule, and just like the left hand rule, it involves the F, which is the force. Okay, so the force will then no, actually let me put it this way. Let me start with your hands on the right. So your thumb will represent, just like the left hand rule, it's always the force, and then your index finger, just like the left hand rule, is the magnetic field. And then the last one, the middle finger. Now that's just like the left hand rule, that's gonna be your current. Okay, so once again, we've got your F, we've got your B, and then you've got your I. Now let me grab a picture so that we can demonstrate this really well. Okay, so here we go. Then what we have here then is Fleming's right hand rule. So you take your right hand just like that, and as you can see here, let's use their example. You've got the North Pole here and the South Pole, right? And then so the field is moving from the right to the left, like that way. Remember, the field is electric field is the index finger, okay, the magnetic field. Okay, so it's going like that, and motion is going up, so which means current is coming towards you like that. Okay, now let's take a look at my example over here. So in my example, I've got the same configuration, and then let's say they ask you now from, okay, let's A, B, C, D. Let's start with CD. They tell us that the force is moving up this side. So if your magnetic field is moving that way and your force is moving up, that means the current is coming towards you. Okay, so here, this is how we make electricity there. So it's coming towards you and going that way. Now if we look at side AB, okay, so if this thing is turning anti-clockwise, then AB is moving downwards this side. Okay, that's the force, it's moving down. So let's see which way current is moving there. So magnetic field is still going that way, but now the force is not going up, which means my thumb must face down. The only way I can do that is if I do it like this, turn my finger like this. This is the right hand. Okay, so my force is going down, my field from right to left, so which means my current now is moving inside towards, you know, towards the paper or towards the screen. So it's moving that way. Okay, so it's moving that way. Okay, so that's it. Now when it comes to generators, okay, so this is just a rule to figure out where all those variables go. But when it comes to generators, remember, motors is only really just one kind, but generators are a little bit complicated. You know, we have kinds of generators, okay, and we need to know there's generally generators. There's generally two kinds of generators. The first one is what we call the AC generator, which stands for alternating current. Okay, the A stand current. Yeah, the A stands for alternating, and then the C stands for current, and then we also have DC. The D stands for direct, and then the C stands for current. So we've got a direct current over here. Now let's see examples of this. Now, what does the AC look like? So AC looks like this. You've got your wire, okay? So let's draw the wire again. That is moving, that's rotating due to mechanical energy. And then AC, the difference with the AC is that connected, remember here, for a motor we had electricity or battery or whatever, but for this now we have a what we call, okay, this is a ring, but what kind of ring is it? This is what we call a slip ring. Okay, slip ring. Okay, that's what you have for AC, and then connected to the slip ring, then you have brushes, you know, that actually transfer the electricity. So this is just a brush. Okay, and then now let's look at the DC. The DC, same wire. Okay, now for a DC, let me just make it a little bit bigger. Make it a little bit bigger. Okay, I need, okay, so you got the same wire, and then instead of slip rings we have what we call a split rings, which means it's a ring but it's split like that. Okay, so it's still a ring but it's split. So this is a split ring. That's the difference between a AC and a DC. It also has brushes, you know, attached, whatever. Okay, but really the difference between AC generator and DC generator is that AC has a slip ring while a DC has a split ring. Okay, I hope you understand that. You will need to know this. Okay, so now let's talk about what I'll call perhaps the equations that are used in this topic. Equations or formulas or formulae. Okay, the formulas that are used in this in these things, and I'll start with the DC. Okay, so for a DC, if you have an EMF volume, I mean, listen to me saying EMF volume, voltage, and you have it against, you know, time, really, what happens is that the voltage in a DC is that because it's split, it goes, let me just do this, the voltage, it just swings, it goes up, comes down, it goes up, comes down, you know, so it's got a maximum voltage there. Okay, I'll call it Vmax. My max is not very pleasant, but I'll call it Vmax. So that's the maximum voltage. Okay, but so okay, hold on. The formula that you need for this is actually the average voltage is equals to Vmax. Remember, when we're talking about average, you take, say, maybe two variables and then you divide them by 2. If you take 3, you divide it by 3. So here, let's take the maximum and the minimum. Okay, so you take the maximum plus the minimum is 0, right? And then you divide it by 2 to get the average. So then your V average is basically just your Vmax divided by 2. That's it. Okay, that's what that's all I need you to know at this point. That's all that is required for you to know about the DC generator. Okay, for your how you calculate your average voltage. Now let us look at the AC now. Okay, now when we look at the AC generator, okay, so what happens with the AC generator is that, well, let's have the same configuration. Let's have over time what happens. So AC behaves like this because it's alternating. It goes up and it comes down and then it goes up again and so on and so on. So it keeps alternating like that. So here really this is your Vmax, or rather your positive Vmax. But also down over here we have a negative Vmax. Okay, so what happens is that when you're trying to solve your average V, you're gonna say positive Vmax plus the negative, Vmax divided by 2. Still taking the maximum plus the minimum value. And what happens here, you find that it adds up to 0. So that's not going to help us. Okay, so let's look now at the voltage we've looked at. Now let's look at the current. Maybe that will help us. Let's see. If you take the current, then you'll find that the current also behaves like this, exactly like the V. Okay, the voltage, where you have current, your positive maximum current, and your negative maximum current or minimum. And then you'll find that even the current, your average current, is still going to be 0, because you add these 2 up and then they add up to 0, which doesn't really help us. Okay, but now, so when we put this into perspective, it doesn't help us at all. So what do we do? So we then express voltage and current, both of them, because they're behaving the same way. And current in terms of what we call the root mean square. root mean square. What's this? RMS. Okay, so that means that we go, instead of using the average voltage, we use the RMS voltage, and that's equals to the maximum voltage divided by the square root of 2. Now I can derive this formula, but that's not the purpose of this lesson. Just want to demonstrate to you quickly that these the variables that we use, and tell you and show you why we have to use them, because the average voltage is 0, so then we have to resort to what we call RMS. Also, we use the RMS current, where you can take then the maximum current and divide it by the square root of 2. Now this is in your formula sheet. Okay, like I said, I'm not going to derive it, but I can. It's just that I didn't want to, derive these things. I wanted to show you why we use them. I think that's more important to know. So this means if you go to your formula sheet once again, and look at some more formulas, you'll find that actually the formula for power, average power, so that you can be charged effectively by ESCOM. Oh, by the way, ESCOM it produces AC, alternating current, and then sends it out. The current you receive in your home is AC current, and how they charge you is that they use the average power, and that's how they calculate it. They take the RMS I and multiply it by the RMS voltage. Okay, power is equals to I times R. Okay, there's 3 formulas. The second one for power is I squared, and that's the RMS one, times R. And then the third one is voltage squared, and it's the RMS voltage divided by R. Now, which formula do you use? You use the one that is dependent on the question, on what you are given in the question. So you choose the one that has the given variables in your question. Now let's just go and see how these principles actually apply in an exam setting. Okay, so this question says that the diagram below is a simplified representation of a DC motor. Okay, the current in the coil is in the direction X, Y. Okay, so X, Y, I see X, Y, there it is. So the current, we're given the current, and we know by definition the magnetic field is always moving from north to south, so that's the way it's moving. Now number 1, 10.1, okay, 10.1.1 says name the component that ensures that the coil rotates continuously in one direction. Remember, in DC we spoke about that it has split rings, and you can see them here. Actually, these rings are split in the diagram, so we'll call that split rings. Okay, and then the next question, 10.1.2, let's change the color. 10.1.2 says In which direction will the coil rotate? Write down only clockwise or anti-clockwise. Okay, so let's look at this. What are we dealing with here? A motor. And remember, a motor, we use the left hand rule. Okay, so we've got, let's start with the current. It's moving towards the screen, so it's moving like that. And then, but now our what do you call this? Our magnetic field is moving from north to south, so our index should point that way. Okay, so which means my finger must now, and the thrust is moving downwards because my current is moving towards you. For you, it's moving towards the screen. It's moving towards the screen, and then north to south from left to right. That's my magnetic field, which means this side, the thrust is moving down. So if it's moving down, okay, let's do this side. Let's just name this side AB, just for interest sake, to make sure that we got this right. So current now is moving this way, and field is moving that way, so thrust is moving up. That's my thumb, so it's moving up. So what's happening here? This thing is not moving like a clock, so it's moving anti-clockwise. Remember, a clock moves from 1 to 2 p.m. to 3 p.m. This one is moving the opposite direction, so this is anti-clockwise. Anti-clockwise. Cool. Write down the next question. Write down the energy conversion which takes place while the motor is working. Now, we spoke about this, about a motor 10.1.3, that actually a motor, what it does, you can actually see here, there's a battery connected right over here. Got positive this side and negative this side. So it converts electrical energy to mechanical energy. Okay, so that's what it does, to mechanical energy. All right, let's read the next question. It says, in an AC generator, now we're speaking about a generator, not a motor anymore, producing a maximum voltage of 320, is connected to a heater of resistance 35 ohms. Now write down the structural difference between AC generator and a DC generator. Well, we just spoke about this. Okay, so 10.2.1, okay, is that the difference is that a DC generator has, okay, split rings, and what's the other one? The AC generator has what you call slip rings. Now, how do you remember DC now and AC has split? The reason, if you look at this ring, this looks like a D right over here, right? This one here, this looks like a D, right? So, and then that looks like a C. You got a CD, a DC. So DC always has a split ring. So you've got a D and in the structure of it, and a C. Okay, so which makes it a split ring. That's how you remember DC split. So that's how you remember split ring. Okay, anyway, that's just a side note. Now it says calculate the root mean square value of the voltage. Now we're talking about 10.2 2.2. Now, what is the formula for the root mean square? We just spoke about it for the voltage. Vrms is equals to Vmax divided by the square root of 2, right? So what is our Vmax? Our Vmax, we've been given maximum voltage is 320 divided by square root of 2. Now, if I put this in a calculator, I'm going to get a value of 226.27 volts. You can go ahead and try it with your calculator and see if you get the same answer. Okay, let's check the next question. The next question says calculate the root mean square value of the current in the heater. Okay, so now we're looking for the current 2.3. Now we know the current RMS is equals to the maximum current divided by the square root of 2. Now, do we have the maximum current? Let's go see. No, we're not given maximum current, but we can calculate it according to Ohm's law. Okay, we can calculate it according to Ohm's law, and Ohm's law just says if you manipulate it, it's I is equals to V over R. Okay, so let's say that's Imax. We're looking for Imax, so we use Vmax as well. So what's our Vmax? We've been given 320. That's our Vmax divided by our R. What's our R? We've been given is 35 ohms. So 320 divided by 35, you put that in a calculator and you will get 9.14. Okay, so amperes, that's Imax. And then having after then solved your Imax, you can then come back. Actually, let me write it this side. You can then come back to our RMS, because now we have the variable that we needed, which is Imax, and Imax we just solved to be 9.14 divided by the square root of 2. Put that in a calculator and then you'll find that you get 6.46 amperes. There we go. That's our final answer. Okay, that brings us to the end of our session. I hope you understood everything that we were doing together, but in the event that you didn't, please do contact me on my website, which is www.mvtutors.co.za, or alternatively you can connect with me through my WhatsApp number, which is 076-312-1107. Now, before you do contact me, please speak to your parent or your guardian, whoever will be paying for this session, because remember, for me to tutor you, it needs to be paid. So the person that will be paying needs to be involved in this process. Okay, other than that, that's it for me. It's goodbye, and I appreciate you.